Okay, it's 12:20 and welcome back. Thank you very much, everyone. Our plenary speaker for today is Brucek Khailany. He is at NVIDIA, where he is the director of the ASIC and VLSI research group. Brucek got his PhD from Stanford University, and Brucek is a classical pianist. So I look forward to the Rachmaninoff recitation at the end of this talk. But thanks very much, Brucek, for giving our plenary talk for today. It's all yours.
Thanks, Paul. And also, I was in Iceland in 2007, and it's too bad that I couldn't be back there for this talk. But thanks to the organizers for inviting me. So I'm happy to talk to you today about the work that our research group at NVIDIA is doing on applying machine learning to our chip design methodologies and some visions for the future. So the research group, oops, I need to share my screen. Can you see that?
Yes, we can. Thank you.
Okay, great. Yeah, so the research group that I manage is one of about a dozen research groups at NVIDIA Research. We're just about a few hundred full-time researchers distributed across a number of sites in North America and Europe. And we work on problem areas ranging from AI to graphics down to how we build chips and systems, so architecture and VLSI. And our group focuses on VLSI design methodology, digital VLSI circuits. And some of our more famous recent works are shown at the bottom of the screen here. Most relevant to this talk, we're doing work both on deep learning inference accelerators, but also on how do we apply machine learning to EDA. The research goal that this is in support of is this issue of chip design complexity and improving our chip design productivity. So if we go back a few decades to the beginning of Moore's law, we were able to exponentially add more transistors every few years to our chips. And that increase in transistor count allowed us to provide more chip capability and a measure of performance to customers. A few decades ago, we stopped being able to add that chip capability on an exponential growth curve at fixed power once Dennard voltage scaling ended. And within the last decade or so, the ability to provide that capability at fixed costs has started to end, as well as the sort of traditional Moore's law transistor scaling, density scaling at fixed costs has ended. However, customer demand for more compute is continuing to go up. And that trend has one of several drivers that's really led to higher chip design complexity. So as we meet this desire for more performance, we keep adding more transistors, but we're not just taking simple cores and replicating them. We have to add more and more complex cores. We have to add a lot of specialization and accelerators to provide the performance that people need. And on top of that, in order to make our transistors work with 7 nanometer, 5 nanometer, 3 nanometer below, there's a lot more complexity in terms of design for variation, design for manufacturing. And so our belief is that in order to tackle these things, we need to do even more automation than we're currently doing in the EDA space to keep up with these demands. At the same time, what also is happening is there's these macro forces that are shaping computing today. So starting a few decades ago with the introduction of the GPU, we've seen this accelerated computing model take off, where rather than just having your programs that are optimized for latency on a single core be the predominant way of running performant computing applications, people have started moving to this accelerated computing model where you have accelerators such as GPUs or other types of accelerators that are good for parallel processing or certain types of workloads. And that has been one of the factors that's helped fuel the rise of this deep learning revolution, where rather than hand coding algorithms for specific tasks, we can instead have general purpose learning algorithms and just feed these learning algorithms with tons of data to have the computer basically learn a task such as classifying images or recognizing objects in the vision vision perception space. And these two trends have kind of fueled each other as our GPUs have gotten better at doing deep learning and broadening the areas at which you could do deep learning. It has enabled things such as, for example, transformers and conversational AI as being something that's practical to deploy in real production environments. And so it's sort of a virtuous cycle of our accelerators getting better for deep learning, and people are able to use deep learning in more and more areas, and so forth. So, and it's not just in research. I mean, we're seeing that this trend in AI is transforming many industries. So people are probably familiar with the on the top row, image classification, image recognition, conversational AI, speech and voice, as well as recommendation engines, which are basically the workhorse behind the internet economy these days. Perhaps less familiar to people are all the other industries that are also being affected by AI. In healthcare, AI is helping with diagnostics, infrastructure and public safety markets, as well as industrial markets for things such as anomaly detection and so forth. So it's logical to conclude that AI is going to also transform our industry in terms of how we build chips themselves. And so that's the research question we've been tackling. We're already seeing quite a bit of interesting progress here, both in terms of direct GPU acceleration and applications of AI. On the design side, there's been a lot of recent work published on design verification, place and route optimization, hotspot prediction, GPU accelerated computational lithography. Also on the manufacturing side, the areas shown here, as well as on wafer inspection and test, which is essentially processing very high resolution images of your manufactured chips. So how do people go about doing this? So, well, I like to think of machine learning as this tool, or really a set of tools in a toolbox that engineers, in much the same way that programming languages were a tool that every engineer uses in the past. Now machine learning is a new set of tools that every engineering group is going to be using in some way or another. And the work we've been doing on the EDA side, there's kind of three different areas where we've been applying learning techniques. So one is what people often think of as this deep learning revolution today of using supervised learning, where you have millions of examples and you train a neural network model to learn some function based on labeled examples for what the correct output for each input should be. The challenge with this supervised learning is it really requires like millions of examples, often maybe hundreds of thousands to millions of examples. And so curating these data sets is the hard part of doing supervised learning. Actually, the model, figuring out the model to use is probably much easier than basically the feature engineering and data set curation, that part of it. The second learning technique, which is probably familiar to most people in the CAD community, are sort of auto-tuning type approaches such as Bayesian optimization, where we are trying to minimize or maximize some objective for a black box function, and we're trying to figure out what inputs optimize that objective. So this technique is pretty suitable for things such as parameter or knob tuning, and isn't necessarily a new technique, but something that's, I think, having a little bit of resurgence in our field. And finally, a newer area that is just kind of emerging as something that could be quite interesting is the application of reinforcement learning, specifically deep reinforcement learning, to optimization in EDA. The idea behind reinforcement learning is that you train some agent. Typically with deep reinforcement learning, that agent is based on a deep neural network model that recommends some action based on to perform on the environment. And the environment returns some reward saying whether or not that action was good, as well as the state of the environment. So this has worked really well DeepMind has done all this work showing that deep reinforcement learning works well for playing Atari games and for playing Go and chess. So basically where you have a very constrained environment with a limited set of potential actions that you can place, it turns out you can train these deep reinforcement learning algorithms to do better than other combinatorial optimization algorithms. And if you can figure out a way of sort of treating your EDA problem like a game, deep reinforcement learning seems a pretty interesting tool to use. So in addition to learning techniques, the other question is what models, what deep neural network models or neural network models should we use? In our group, we kind of, I think, kind of segment the world into kind of like 3 categories. So one is when we have less structured data, where we have inputs that may be things like performance monitors or just vectors of features. We often can use just fully connected layers, or also known as multi-layer perceptrons. And our standard sort of baseline model that we often use is XGBoost, which is a gradient boosting tree model. These work pretty well for a lot of machine learning workloads. They're fast to train. They're good at predictions. When you have 2D data that can be represented as an image, basically on an XY grid, it's commonly known that convolutional neural networks work quite well, where you basically have these convolutional filters that can look for spatial patterns for between neighboring pixels in these images, and you can make some prediction or do some classification based on image data. So this in EDA, this is obviously the place where we have images is most often thought of in digital backend design, where after you go to placement, you can think of all of your data being laid out on this XY grid, and you can treat things as images, such as the paper we just saw on DRC classification earlier. And more recently, what we've been really excited about in our group is this newer model that has emerged just within the last few years called graph neural networks. And so the idea with graph neural networks is if your data is naturally structured as a graph, rather than looking for patterns in your data that are spatially correlated on a 2D grid like an image, you can look at patterns that are related to a node of a graph and its sort of nearest neighbors, or maybe 2 neighbors away in the graph. And these allow you to do things like classification on graphs or other types of regression problems and so forth. And this is exciting because, as most people also know, in EDA for digital logic or for analog logic, before we go to physical design, our data, basically logic netlists, are naturally structured as graphs. And so these techniques seem like they're quite applicable for those types of problems. And I'll talk today about some of the work our group has done in applying graph neural networks to EDA. Okay, so the last piece, now that we have models and learning techniques, we need basically a way of doing the engineering. So at NVIDIA, we make a lot of hardware for accelerating deep learning. Most recently, we've just, earlier this year, we've announced our Ampere chip, which has 300 teraflops of performance on training, and it's available in a lot of the public clouds for doing training work. And then you can do things like run your models and train them on a single GPU card or scale up to multi-GPU data centers. So this is a key enabling factor for being productive with your research, because we often need to tweak hyperparameters in your network and try to get results and back as quickly as possible to adjust things in our designs of our networks. And then the other cool part of using this toolbox for doing engineering is there's just a huge amount of open source software available to anyone who wants to use it for applying these models for these problems. So essentially, it's not that hard to code up models for doing, let's say, graph neural network machine learning. The hard part is, again, curating your data sets and making things work. So, I'd now like to just talk about some of the examples from a few recent examples from our group of applying machine learning to predictors in chip design. So this is similar to what Andrew Kong had talked about earlier this morning, of basically point tools that can be used for predictions in combination with existing EDA tools and flows. So the first example is from the realm of microarchitectural design space exploration. So this is work published by Ranga Venkatesan in our group at ICCAD last year. So we have this framework for a highly configurable neural network inference accelerator called Magnet that is written in high-level synthesizable System C, C++ code. So it's highly parameterizable with the number of various hardware configurations being an option, as well as it's intended to work as a tiled architecture where you have an array of processing elements. The details of what's inside this are less important to what I'm going to talk about here, but the key thing to understand is that there's this huge design space of how you build each PE and how you spread your workloads in the form of neural network layers during inference across your PEs. And it turns out that the way that you map these workloads onto the design, it can be very different in terms of performance and energy, depending on the different mappings. And so the sort of typical way of doing this is you'd try to create some pruning heuristics to reduce your map space, and then try to just search around for all the possible ways of doing both the hardware implementation itself as well as the mappings. But a very simple application of machine learning here that we used was to just put this into a Bayesian optimization framework for trying to figure out, given the objectives of minimizing energy in the form of picojoules per operation and performance per area in the form of teraops per square millimeter, rather than sort of exhaustively search the design space, can we just do a smart search of the design space to find the optimal mappings for optimizing these criteria? It turns out Bayesian optimization works pretty well in about 100 runs of going all the way from our source C++ and our mapping files through high-level synthesis, logic synthesis, and gate-level simulation and power performance analysis, that we could basically find our optimal designs much more quickly than we could with basically exhaustive search, random search. And after doing this paper, we separately asked ourselves, could we do better than this? Because it still takes quite a bit of work to find all those. Not everyone's going to have access to as many licenses as we may have for HLS and logic synthesis and so forth internally. So the other thing we thought of is, well, it should be easy to just train a model to essentially predict the performance and power for each of our mappings if we had the data. So it turns out we actually do have a lot of data already, because we have a constrained random functional verification suite that basically just generates random hardware mappings on random with random layer parameters, which always get simulated through RTL because we're doing functional verification, and then the cost of doing power analysis of that is trivial, because you just need to capture your activities into a save file and run that through power analysis. So we essentially have training data from that constrained random verification suite. If we do a little bit of curation on it to make sure it has like good data balance, we can train very simple models for predicting power and performance of our hardware accelerator just from a few simple features of how that workload, the characteristics of the workload, how it's mapped on the hardware, and so forth. And this is one of those examples where something like XGBoost just works really well. We don't really need to do a more complex model necessarily. But we did try a multi-layer perceptron as well. I mean, it performs pretty similar to the XGBoost. But a very simple linear model where you're requiring all of your performance and power metrics to be some linear function of your features doesn't perform so well. So this was just one quick example of how we've been using machine learning internally. Another more complex example, moving to the physical design domain, I think Andrea had hinted about this earlier, is some work we've done on routability prediction. So the idea here is that ideally, if you could predict routability issues earlier in the flow, you may be able to constrain your downstream tools and get better QOR. So there's two. Is there a question? Or someone may need to mute. Okay, so the work on the left was work we did jointly with Duke, Jiaoxi, who's a student there at Duke, worked on an idea called RouteNet, where rather than just take the result of placement and look at global routing results and overflows and so forth, and heuristics for predicting where you might have problems after detailed route with DRCs, perhaps you could do better by training a convolutional neural network to essentially analyze an image of all the global routing overflows and other information in the place design. It turns out you can get a better accuracy using this model by about 50% compared to these heuristic-based methods at predicting where you are going to have DRC problems. So a next step of this might be to, for example, feed this back into a placer and have it sort of modify the results to get better overall QOR. And then going back to what I was talking about earlier with graph neural networks, in our group, we also were wondering if could some of these congestion problems or routability problems just be directly predicted from looking at the logic net list without having any information about the placement itself. On the left, you can see the actual congestion from a partition, and on the right, you can see a prediction that was made from using a graph neural network called a graph attention network, where we just tried to train using ground truth data on basically the logic net list and information about each node and its neighboring nodes in the graph. So it turns out you can actually predict pretty well when your congestion is correlated with certain types of digital circuit topologies, for example, like high fan in muxes and things like that. It's not going to find all congestion problems, for example, like issues related to macros, routing around macros and stuff. It's not going to find those, but this can kind of flag things earlier in the flow, which is important in our case because we often do many rounds of synthesis before we ever have a chance to run things through physical design. Another example of how we're using graph neural networks is on power analysis. So this is work by Yanqing Zheng, who in our group, who developed an idea called GRANITE, Graph Neural Network Inference for Transferable Power Estimation, published at DAC this year. The problem he's tackling is, typically for power sign-off, we do exact gate level simulation. You run through gate level sim, ideally with delay annotation, take gate traces, and run through a power analysis tool from a commercial vendor. This is highly accurate, about as accurate as you can be, short of running SPICE, pre-tape out, but it's very slow, especially if you have a very large chip or even many large partitions from a large chip. What's often done is averaging your switching activity over some window at like register outputs, and then propagating those probabilistic activities through the net list. The reason this is often done is, for example, you may have RTL simulation results where you have basically activity levels at the outputs of your RTL flops, but you may be manipulating the net list during synthesis or during downstream place and route runs. And so to actually have a power estimate, you need to basically just propagate that very quickly. The problem is that these switching activity estimator approaches based on those probabilistic propagations are notoriously inaccurate in certain types of combinational logic due to a number of factors. So the question we asked is if we could use graph neural networks to improve that switching activity estimation. It turns out it works pretty well. So the idea is that we have one graph neural network model that we train on ground truth toggle rates to understand how typically the activity rates can propagate from inputs through a combinational logic net list. This trained model can then run inference on a brand new net list that it's never seen before. So the cool thing about graph neural networks is they can infer on new graphs that they haven't actually seen before, not just new workloads on the same graph. And this leads to pretty fast and accurate statistical activity estimation. The architecture of the network is you basically take, the way it works is you take a combinational logic net list, transform it to a graph, and then you have in the architecture of the neural network model has first a fully connected layer for doing encoding from some number of features to basically a vector of embeddings, and then you basically have a number of graph neural network layers that basically do message passing between neighbors in the graph node for basically modeling the effect of neighboring nodes in the graph, and then a final fully connected layer for mapping back to whatever your output is, for example, learned toggle rate in this case. This worked pretty well. So compared to a baseline design that's similar to what commercial tools do. Our baseline switching activity estimator had about 30% error on a number of pretty simple combinational logic netlists, but this graph neural network could get the error down to 3 to 5%. So this means you could sort of use this as a replacement for gate level simulation if you wanted pretty accurate switching activity estimation. And at the same time, you can get orders of magnitude. It can run, basically doing an inference on this graph neural network can run orders of magnitude faster than actually doing the ground truth gate level simulation. Another example where we've used graph neural networks is in analog layout. So here, the problem is that especially in FinFET, modern FinFET technologies, parasitics play a huge role in the performance of your analog circuits. And often what happens is because of this, designers will have a schematic and then they basically do a layout iteration, and the results post layout after doing layout parasitic extraction are dramatically different than what they had after the version of their schematic, and they need to do basically a number of iterations. So ideally what you'd want is the ability to predict the parasitics after doing layout, and so that you can sort of close the loop on circuit simulation post schematic first before you go to layout, and then avoid these iterations. And what's done internally at NVIDIA and in most places in the industry is to use heuristics. So for example, like the number of device fingers connected to a net is a reasonable heuristic to use for like wire parasitics. So the idea that Mark Wren did, and Mark's attending here today, is to see if we could use supervised graph learning to model the effects of like more complex structures in these designs. And his proposal was to map circuits to heterogeneous graphs. So now instead of, we don't have logic gates because this is for analog, but we basically map transistors to nodes. And then we also need to actually map wires to nodes as well, because it's just easier to kind of handle heterogeneous graphs than it is to do an inference on an edge. Once you do that, you can basically use something like a graph convolutional network for, again, aggregating the information from your neighbors. And you can make predictions about these parasitics in your design. So it turns out on the left, you can see we always, and generally, as I mentioned, we always usually try to compare to a simple model like XGBoost. So this graph on the left shows the mean average error for estimating parasitics normalized to XGBoost. So you can see the linear model when you basically map all of your circuit features to some linear model. The error is quite a bit worse than XGBoost, but the model that Mark proposed called Paragraph, which is based on this approach, does quite a bit better than just a simple XGBoost gradient boosting tree model. And then the real way of evaluating how we're doing is actually to go back and look at the simulation results with these estimated parasitics. So on the table on the right, you can see if you just had 0 parasitics, you had like an average error of about 38% of the layout without parasitics compared to a final layout on a number of designs that we tested. And then when you look at the designer's estimation based on those heuristics, it wasn't actually much better. But with this paragraph model, we could get the parasitic, the simulation errors way down to less than 10%. So this is pretty promising. And more recently, we worked with an intern, Mingji Liu, who is going to be publishing a paper at DATE in 2021 that basically takes the paragraph model and takes the embeddings from the graph neural network directly, and then feeds them into a Bayesian optimization framework for trying to basically do automatic sizing with this graph neural network-based parasitic prediction. And he had some cool results that show that you could sort of do auto sizing using this graph neural network parasitic prediction and do optimization on analog circuits that way without even having to do layout. Okay, so that was an overview of some of the more recent work in our group. As you can see, we're pretty excited about graph neural networks because they seem to be pretty applicable to the ML for EDA design domain, and it's exciting to see other groups also publishing using that. So let me talk a little bit about where we see the future research opportunities, and perhaps give some ideas to the research community. So the first observation, as I mentioned, is that a lot of the work for doing all the work I talked about is all in the data sets. It's feature engineering, curating your data sets, avoiding data imbalance problems, false positives, how do you cover the design space. So just one observation in all these other fields where people have made a lot of progress in AI, it seems like they are greatly benefited by having these large open source data sets and benchmarks that everyone standardized on. So ImageNet was kind of the first for image recognition. There's an equivalent one for object detection and autonomous driving. And most recently in conversational AI, people are using like self-supervised learning on basically all of Wikipedia to do their training. And then there are these smaller data sets such as SQuAD, which is a Stanford question and answering data set for evaluating their conversational AI workloads. So these efforts have actually typically been led by universities, and both in terms of collecting the data, perhaps using Mechanical Turk if they need to or something, or publishing the data sets, dealing with rights issues and so forth. So I think there could be an opportunity to pursue something similar for EDA. I mean, we're starting to see that there's quite a few open source designs out there. There's open source tool flows. So if we can sort of, standardize on some set of designs, open source data collection, format analysis, and establish standard benchmarks, I think that's something that would benefit the whole industry, both research as well as people sort of looking at deploying ML for EDA in production. The second area that we've been thinking about as future work is, I think, aligns somewhat with what Andrew was talking about this morning, which is, so far we've used machine learning more as predictors that augment existing flows. But we're starting to see evidence that we could use, especially tools such as deep reinforcement learning, to do optimization to either augment existing known algorithms, or perhaps even replace handcrafted heuristics in many EDA tools, or automate tasks where previously we haven't seen that that automation has worked compared to, say, like what human intuition. So for example, in the areas of custom layout, there's some evidence that deep reinforcement learning may be able to outperform humans, or at least do just as well as humans, whereas traditional combinatorial optimization algorithms such as stat solvers or integer linear programming solvers haven't been able to necessarily be as successful. And a lot of this comes from the fact that reinforcement learning can kind of learn from experience and recognize sort of visual patterns rather than requiring, let's say, mathematical formulations of your problems. So it's a lot easier to set up, and it's a lot easier to kind of like in practically use, especially as you move from one technology to another. And with deep reinforcement learning, the idea is, I mentioned, you have an agent that's recommending actions and receiving rewards from the environment. Typically, the agent itself is based. A lot of the models that I talked about for doing the DNN type of models for doing prediction are very similar to the models that you would use in a DRL engine for doing like a value network for predicting what the state of the environment might be. Okay, and then the final area that we've been thinking about and think is an interesting area of research is moving from these point-based predictors to an end-to-end AI-driven backend flow. So the baseline flow that we use today is shown on the left, where we have some synthesis netlist that we push through placement, CTS, and routing. And this may take days to weeks on a large design. A human has to kind of analyze the QR, go back and adjust macro placements, tool knobs, timing constraints, et cetera, et cetera. And eventually, once you get the right set of all those things together, the tools work well, and you basically have a pretty good design, and you hope to basically close things first and then have some time to optimize QR. Well, we're at the point where I think we can start thinking about automating this first step using an AI-driven physical design flow. So the idea here is that rather than having a human in the loop sort of analyzing those results and going and doing that optimization. Ideally, what we'd like to do is have many tens of thousands, hundreds of thousands of iterations of trying out the whole design space of potential physical implementations. In order to enable this, there's two things that we don't have that we currently need. So one is fast synthesis and placers. So if we want to run hundreds of thousands of iterations to get a deep reinforcement learning loop to work, we need to run placement every single time. And fortunately, there's been some work in this space on using GPU accelerated placers. This is work we've done collaboratively with UT Austin and Peking University on DreamPlace and ABCD Place that allow us to basically place large partitions of millions of cells in seconds or minutes, which is fast enough to start perhaps throwing it into these reinforcement learning loops. But the other problem is once you have a placement, we can't really predict with a lot of accuracy what the QOR will be downstream after you go through clock tree synthesis and routing. So we still need better predictors in order to make this loop work. So we need some sort of keep needing more accurate quality of result predictors. And the question arises, like, what labels do you use for those predictors when you do the training? If you're just basically trying to predict whether you have a timing violation, it's probably not that great of a predictor because the tools do a great job of fixing timing violations. So the question is like, how hard does a tool have to work to fix timing on a certain path or to work around congestion issues and so forth? So in order to do that, we need to figure out what labels to use, get sufficient training data and so forth. But once we have all these pieces, I think it's possible to put all this work together and to apply deep reinforcement learning to improve our automation and quality of results from our final designs. I think I've gone a little bit over time, apologize about that, but just to summarize, our viewpoint is that accelerated computing and AI are transforming many industries. And a lot of the work we're doing in our research group and other research groups at NVIDIA is all about applying AI, not just enabling our customers to use AI, but also applying it internally to our own products and product development processes. I think ML and AI in general is a new tool for chip design that I think can probably be used everywhere in our design flows. And we're excited about future tools combining traditional algorithms with ML-based optimization and predictions. So a lot of this work is in an IEEE micro article that has just been published. So if you're interested, I can encourage you to read those or check out some of the publications on our website. So with that, I'll wrap up. Thank you very much.
Thank you very much, Brucek. Are there any questions, please? I've got both the chat line and the Slack page open.
Yeah, I'll bring up the Slack myself.
Okay. While we're waiting, you talked about automating the layout.
Yeah.
And do you feel that's doable for an open problem, or only doable for constrained problems, such as a particular type of design?
Are you talking about automating custom layout?
Automating custom layout, yes.
Yeah.
Yeah, go
on. So we have, actually, there will be some work. I think Mark Wren is on the line, but he's been working on automating standard cell layout using deep reinforcement learning. And I think there's some work that I'll be talking about at NeurIPS on this and as well. But it may be, at least for now, it seems like, given some reasonable constraints that are similar to the constraints that designers use in modern FinFET technologies, that it seems doable. Like, obviously, if in other words, you probably need to constrain things to like something that's standard cell like, but it turns out when you go to like FinFET, 7 nanometer and below, you kind of need to do that anyway, even for analog. Like in the old days of analog, you kind of do anything you want, right? But now you kind of need to put things on grids. You need to kind of like have a standard power strap between VDD and ground, and like say, okay, I'm going to put my NMOS here, my rows of NMOSs here, my rows of PMOSs here. So that kind of like highly constrains the design space enough that it seems like it's tractable for DML type solutions to work. I mean, it's probably like the right solution is probably not going to be just like throw the whole thing into a DRL engine. Like a lot of the work may be like DRL working in combination with known algorithms for maze routing and so forth, for example.
So I noticed the example you chose, you illustrated with an eye diagram, which implies to me as a SERDES. Is that your main focus? Or do you think you can extend this to millimeter wave circuits and more complex creatures like that?
We haven't looked at those. I mean, obviously we care. We're not, you know, we're focused a bit more on the circuits that are more related to NVIDIA's products right now. Yeah, I mean, I expect over time we'll learn more and more, and it may be the case that it would apply to even more. I would be hesitant to say no because I mean we keep getting surprised with, you know, how well this stuff works once you kind of figure things out.
Right. And I don't know if you have the chat line up, but there is a question there.
I don't. I'm trying to figure out how to.
It's on the bottom, but I can read it to you.
Yeah,
from Israel. Curious, what type of graph models does one typically use for representing hypergraphs, i.e. complete graphs, star models, etc., when converting them into graphs to apply GNNs and GATs? The chat's at the bottom of the screen if you move the cursor near the bottom.
Yeah, okay, I found it, yeah. Let's see. I might see if Mark is online and wants to take that one. Do you want to? Mark, are you online?
Sure. Yeah. Okay. Yeah. So the problem with hypergraph is the net has it connects multiple nodes, right? So one of the problems with chip design is usually these nets are like sometimes you have like high final nets. It's very hard to so this distribution of that nodes and the other like a cell nodes or device nodes are like really different. So that's why we actually in the paragraph work we propose to basically treated the nets as like a different type of nodes as a device. So it's kind of like a heterogeneous graph. So you have different type of nodes. You have net nodes and you have cell nodes and device nodes. And then once you create that, then it's no longer a hypergraph anymore, because now you can explicitly describe the hyper edge, which is basically a point node to node edge between the device node and the net nodes, right? So that basically decomposes that problem. So there's no hypergraph anymore. It's become like just a simple graph, and you have to work on the heterogeneous graph. So that's the way we propose to do it. So.
Thank you. Rajiv Jain has a question I believe he wants to ask orally. Rajiv? Can't hear you, Rajiv.
My apologies, I was on mute. Brucek, thank you so much. That was a great talk. Many ways lays the foundation for my talk tomorrow, so I'm very happy to hear it. But a couple of things that I want to ask you with regard to the reinforcement learning, which has attracted a lot of attention because of its analogies to learning by experience and optimization and winning at games and things. And it seems to me that one area where the analogy between playing games and designing chips breaks down is that games at the end of the day are fairly structured. The strategies can be subjective, but chess has a set of rules, Go has a set of rules. In chip design, it's a creative process. Designers make up the rules as they go along. And I see that as a fundamental challenge to applying reinforcement learning. I'm wondering if you've thought about that, and if at NVIDIA you may, because this is an area for specialization, if you maybe thought about advances in reinforcement learning we need that can go beyond learning by experience, but also do this creative thing about making up rules as you go along, which is really intuition in many ways. And I personally haven't found that reinforcement learning as it stands today can really do that. But since you emphasized in your talk, I'm wondering if you guys have figured out something there.
Right. So I guess I'll try to split it into two questions. So one is this question about reinforcement learning, basically like, does it only work if you have sort of highly constrained rules, and it's, it's not maybe not the best thing for where you need to sort of like be creative or some sort of designer intuition kind of stuff. And the second part was sort of what optimizations do we still need for reinforcement learning?
Right.
So on the first one, I think that I think I generally agree with that. And it's not clear that I think where we can see deeper reinforcement learning having a role is going to be in either like alternatives to combinatorial optimization approaches, where like one of the problems with some of the combinatorial optimization approaches for some of these tasks is that you can have like if it doesn't scale well, then you could end up with an issue where the answer, basically can solve something. It can basically say, this is unsolvable, or you could just, it could just not ever finish running. And the good thing about reinforcement learning is like for a lot of these problems, you might be okay with something that isn't necessarily like always finding the most optimal result, but you just want like the best it can do or whatever, which is like a best effort answer. So that's an example. But I do think it obviously you have to like, constrain it to some sort of rules. And so we do, when we've looked at it, we have, thought about sort of, okay, well, how do I think about this as a game? And like, how does the number of potential actions or the action space compare to like a game of chess? Because if it's way larger, then there's a good, or the game of Go or something. If it's way larger, then maybe this is like not the right way of formulating the problem. So that we've definitely like used that analogy and kind of focused on cases where you can kind of think of it like a game. The second question of like what optimizations do we need for reinforcement learning? I mean, so one of the problems is you have to run like hundreds of thousands or millions of trial cases to get this to work. So it's only going to work on problems where so the training side of it's actually like the easy side, if especially you have like a GPU or something to do the training. The hard part is often the environment simulation. So for example, our robotics research group, there's a huge focus on needing to do like all the physics simulation and stuff on the GPU so that you can basically do like virtual training of a robot in a virtual world. So in our case, the environment side of it depends on what you're doing. So like if you're trying to do layout, the environment may be evaluating DRCs or LVS. So that has to run really fast. And if that runs on a CPU and is slow, then it might be hard to train a reinforcement learning engine. So that's an example where we might need, in some of these cases, actually GPU acceleration of traditional algorithms just to make the reinforcement learning optimization loop work. So that's something we've been thinking about, and that's one of the reasons we're kind of excited about these GPU accelerated placers, because it seems like given the huge amount of compute we can throw at the problem, they can basically do kind of placement in the loop as part of your environment simulation, essentially, of decisions that you might make. So hopefully that answers your question, or at least as well as I can.
Oh, thank you very much. Very insightful. I mean, this is the kind of conversation that will go on for a while. So
yeah, it's
maybe I
definitely
hope to catch up with you offline. But thank you. That was great insight. Thank you.
Great. Thanks.
Well, thank you very much, Brucek, and thanks very much to everyone participating. I think that reaches the end of the time slot, but we do have time for one more question since it popped up. And it's on the chat line. How did you foresee defining rewards for place and route using reinforcement learning?
Yeah, I mean, it probably depends a little bit on the problem you're working on, but I guess since you're asking about place and route, maybe you're talking about placing and routing of standard cells in digital partition. So you want it to be tied to the figures of merit you care about. So so wire length, an estimate of the power, estimate of power. Basically some routability metrics, if you're basically talking about, I guess, not final route, but maybe like some, number of DRC violations, DFM type of things. So that's the problem, is like, if figuring out all these rewards takes a long time, and you need to run millions of them to get your deep reinforcement learning to work. It may not be tractable. So often, like what you often do in these DRL frameworks is you may try to have an estimate instead of computing the reward directly, because you can compute the estimate very quickly. And so that could be reasonable. But that's probably an open question and probably an interesting research thing to think about.
So thank you very much, Brucek. At this point, I think we have finished for today. I don't know if our general chairs want to have any final closing remarks.
I think my closing remarks are, well, a big thank you to all the speakers of today. And tomorrow we will start the technical program at the same time as today. And the day isn't over yet. We have our virtual social program. And for this, I hope that Giangia will give us some introduction into that.